Welcome. Welcome back from lunch. Better response? No? Thank you. You're starting it. My name is Akanksha, and I lead the Alliance for AWS at Intel for the region of APJ, and also lead the global HPC as well as AI strategy for our team. So really excited to be here in front of you. I'm also joined by our friends that are sitting up there. I will tell you more about it. But really our session today is to talk about how technology is creating impact for life. We're at reInvent, we're at a cloud conference. How is cloud actually changing our lives? What technologies and accelerated technologies in cloud are actually making our lives come together? And talk to you more about those success stories, talk to you about examples of doing that, and hopefully get a chance to ask questions as well, because we have a very senior panel of people along with me. So really excited to be here. Let's get started. Cloud computing. So how many of you know what Intel does with AWS? Does anyone know about an Intel instance? Go ahead. Which one?
Basically all of them that aren't the Graviton.
That are not, yes, exactly. All right. Thanks, yes. So basically, Intel customizes its silicon to be made available on AWS Cloud. And we have been doing this since the past 17 years. It's been a fantastic relationship. When we start to get that joint engineering journey for our customers, we also want to dive into strategic workloads that are important for us to get the power of our technology to actually converge with the power of cloud. One such workload is high-performance computing. And while HPC, probably about 20 years ago, was meant for education, for research, and for research organizations and academia, HPC today is being severely adopted by the industry. And the collaborations and the research that is being built into observed data is actually making products, services, and everything that we do today come alive. So the rest of the session today will be about how we have jointly worked with customers and partners to drive impact through computing with the power of HPC. As I mentioned earlier, Intel and AWS have a very strong relationship where we jointly engineer, jointly solution, and jointly work with our customers and partners. And HPC continues to be a very strong workload for us. And collectively, we also try to come up with new ways in which HPC on cloud, powered by Intel, can actually make your HPC experience come alive. And so with that, there are a few exciting stories that we have. We have the fact that the AWS Parallel Cluster is part of the Intel Select Solutions catalog. We also have the fact that we are the HPC Partner Competency Badge. So obviously, with this technology, we want to make sure that we are giving that access to all of you. And to your point, the product that is actually being customized on AWS time and time again is our workforce, which is the Intel Xeon Scalable processors. For those of you that were in Adam's keynote yesterday, we also jointly announced the HPC 6ID instance, which is again powered by Xeon specifically for HPC. How many of you know about or work in the space of high-performance computing? Quick show of hands. Okay, you're cheating, Michael. HPC is literally touching every single vertical segment or industry as we know it today. Whether it is designing plans and research for drug discovery, or predicting weather, or figuring out how banks can work better for risk mitigation, or building cars, figuring out how we can do better simulations with crash testing. Everything actually comes alive with high-performance computing, and those days where you needed to have a data supercomputer to do HPC is no longer that. You can do HPC on your laptop as well. And so because it is being severely democratized, collectively with AWS, we thought that in addition to just building those experiences in the industry of how HPC can power through cloud, we also wanted to work on projects that are actually driving technology for good. And so the social impact computing project or program was something that we worked with the AWS team to put together to try and ensure that several verticals like conservation, sustainability, education, water conservation, all those specific projects that are making our lives come together today are supported with the right collaboration from Intel and AWS. And when we started that journey, we obviously needed our special partners as well as customers that are doing these types of research working with us and bringing that as solutions as well as effort back to you. So this is really what we're going to be talking about later today. As I mentioned, in addition to jointly engineering, jointly solutioning, we also want to make sure that technology is improving our lives on a daily basis and is also shaping the future of how technology continues to become democratized for everybody here. So with that, I would also like to quickly introduce the panel of speakers that I have today. I should have done that right in the beginning, but we'll do that in an individual basis. We have Tanner Marsh, who is the associate for the Harvard Cancer Center. With Tanner and his team, we did a whole lot of amazing work around healthcare, and Tanner's going to tell us more about it. So why don't you come on stage? Tanner, over to you.
Hi, so I am Tanner Marsh. I am a master's student at Harvard, and as part of the Wagner Lab at Harvard Medical School, I'm one of the contributors to the Virtual Flow project. And I'm so excited to be here to tell you a little bit about Virtual Flow and some of the really cool work that we've been able to do working with AWS and Intel, both in advancing our own cancer research, but also in democratizing drug discovery at large. So for some background, I'd like to start with the current state of drug development. I don't think I'm going to surprise anyone here when I say that it's really difficult to bring a drug to market. Almost all drug development projects fail, and that means that only 40 or so new drugs make it to the market every year. And of those that do succeed, the whole process from start to finish takes about 10 to 12 years, and it costs $2 to $3 billion. So Virtual Flow is really born out of the motivation to try to reinvent, as it were, drug discovery, which is the first step in the drug development process, and to make a dent in some of the challenges that I've just mentioned. So when I talk about drug discovery, I mean the process of discovering new drug candidates. In our case, that's identifying molecules that might function as safe and effective treatments for a disease. And so what do those look like? Well, a common starting point for new therapies is to find chemical compounds that can bind to and inactivate some protein that is involved in a disease. It's playing a key role in a disease. So in our lab at HMS, we're working on cancer, so we're searching for molecules that will bind to and shut down proteins that are involved in enabling tumors to spread. So if you look up here, sort of visual, you can see the protein on our left might be our cancer target. And it has some active site, which is highlighted in blue. And if we can find a molecule that fits just right into that active site, like a key into a lock, then we might be able to disrupt the activity of the protein. So, but sometimes proteins have structural or physical characteristics that can make it really difficult to find a molecule that's going to bind. And even though we're certain that the molecule exists theoretically, and if we found it, we could synthesize it, it's actually been historically impossible to find some of these. And the metaphor of choice is that it's been like looking for a needle in a haystack when the haystack is the size of Mount Everest. So we know what we're looking for, but how do we find it? Well, basically, we're going to start by taking an entire chemical library, and that's just a set of chemical compounds of different shapes and sizes and chemical properties that, we'll take each chemical in this entire library and test them to see will they bind to our target protein. And so in this light, drug discovery kind of turns into a numbers game. The key point here is that the more molecules that you can test, the higher the chances are that you can find something really good. So traditionally, you had to do these screens in a wet lab, but that comes with a lot of disadvantages. So first and foremost, you're really limited in the number of compounds that you can screen. A traditional screening library has around 100,000 molecules, or up to 1 million if you're one of the largest pharmaceutical companies. And this whole process can cost hundreds of thousands of dollars and take months, which is not good when you're trying to iterate quickly. By contrast, by contrast, virtual flow uses computational techniques. We are able to then screen a 1 billion compound library pretty easily. And this comes with other advantages. Basically, it's much cheaper. It costs $25,000 as opposed to hundreds of thousands of dollars. And the whole process can be completed actually in an afternoon instead of months. And most importantly of all, the scale is so much larger. So to give you a sense of the difference in scale between a traditional screening library and a virtual screening library, you can consider Vermont. And what I mean by that is if the virtual screening library, the 1 billion compound library, were as large as the surface of the Earth, then the traditional screening library would cover an area of about the size of Vermont. And Vermont is great. I love Vermont. But if you never left Vermont, chances are that you'd be missing something important. So the question then that arises pretty naturally is, why stop at 1 billion compounds? And of course, the answer is we didn't. And that's why I'm really excited to tell you about our latest collaboration with AWS and Intel. So we performed the largest known HPC run, and that involved using 5.7 million vCPUs. And that's incredible. Coming from a university, you're used to having a cluster that maybe at any given time you can access 3,000 CPUs. So to go up to 5.7 million is really incredible. And the purpose of this HPC run was to prepare a 70 billion compound library for virtual flow. Basically, the library comes in its initial state as an enumeration of molecules in a two-dimensional form. But because proteins and molecules are three-dimensional objects, you have to convert that to a three-dimensional representation. And so basically, this HPC run is able to have a huge impact on our own work. because if we can screen 70 billion compounds, we are able to find much better molecules for cancer targets, and hopefully that will lead to more potent cancer treatments down the line. But the importance of this HPC run goes far beyond our own work. So that preparation of the 70 billion compound library only needed to be done once. And now the data is available for anyone else who wants to use it. So that brings me to what is probably the most important feature of Virtual Flow, which is that it is, oops, sorry, the slides are a little out of order. It is free and open source. So basically, what that means is that it can make a difference for anyone who wants to do a drug discovery project. If you are an academic group or a small pharmaceutical company, you no longer need access to specialized lab equipment in order to do a drug screen. And what about compute? Well, you no longer need access to a dedicated computer cluster because it's really easy to run Virtual Flow in AWS. So we believe that this project and the collaboration that we've been able to do with AWS and Intel will have the effect of democratizing drug discovery by lowering the barriers to entry, making it faster, cheaper, and easier than ever to find high-quality drug candidates. And the big hope is that that will lead us just a smaller step closer to a world free from disease. And if you want to know a bit more, you can look up the Virtual Flow project or visit the Intel booth 1617. So thank you so much.
Well, hello, everyone. I'm really excited to be here and thankful to our host and our partners at Intel and AWS for giving us this opportunity to tell you a little bit more about the unprecedented milestone that we achieved together in our mission to use cloud-based HPC to accelerate finding solutions to urgent global environmental challenges. My company, Good Chemistry, is a software startup based in Vancouver. We are a team of computational chemists, machine learning engineers, software engineers, and cloud architects coming together with the mission to make the world cleaner, healthier, and more sustainable through accelerating materials design. But why are we excited about this mission? The solution to some of the most challenging problems that humanity faces is bottlenecked by our ability to build better materials faster and cheaper. When you look at climate change, finding renewable sources of energy, building better solar panels, building better ways of and more efficient ways of storing that energy, building better batteries, and cleaning our environment from carbon capture, and fighting diseases. These are all problems that have solutions in material science. By designing new materials with desired properties, we would be able to make progress toward these challenges. Now, why is this such a hard problem? And we learned from Tanner, he beautifully told us about the scale of this challenge of bringing new materials to market. And I think this comparison really shows what the scale of this challenge is. Whenever we want to bring a new material to market, we are looking at a search space of all synthesizable chemical compounds. And the number of possible synthesizable molecules dwarfs the number of atoms in the observable universe. You can see the difference between the numbers. So every time we want to bring a new material to market, we are essentially searching a search space, a solution space that's orders and orders of magnitude larger than our universe. So that's That's why the referral to needle in the haystack problem makes a lot of sense. And that's why we made it our mission at Good Chemistry, and we have engineered a platform called Chemist Cloud that is able to take that large databases of molecules and then break the simulation of these molecules into independent subproblems, spin up large volumes of compute on the cloud to be able to get a very accurate simulation of these molecules at a scale, and to use AI to then predict fundamental chemical properties. Chemist Cloud is in private beta. We already have enterprise users on this platform, and that's our way of accelerating the search through that gigantic search space that we just referred to. So now, all of that sounds good in theory, but we want to see it in action. We want to see an example, a concrete example where we are really using this technology to accelerate solution to a big challenge. With our partners from Accenture, we realized that forever chemicals are an urgent environmental problem that desperately need attention, immediate attention. And that's where we realized that we can use our technology to accelerate solutions to breaking and eliminating forever chemicals from the environment. More specifically, we focused on PFAS molecules. And before I tell you about the unprecedented progress that we made, I want to just take a moment to tell you what PFAS are. So PFAS are man-made chemicals that are very resilient to heat, water, and pressure by design. And they are everywhere in consumer products, in non-stick cookware, in fast food packaging, water repellent rain jackets, firefighting foam, everywhere. There are two problems with these compounds, though. The first problem is that they don't biodegrade. And it's notoriously hard to break these molecules apart. And then the second problem is that they are toxic and harmful for humans and animals. Unfortunately, they compromise the immune system. They can attack the reproductive system. And worse than that, they are actually associated with causing a number of cancers, a number of types of cancers, basically. So they are connected to a whole suite of health issues. Now, to put this urgent problem into context and talk about the scale of this challenge, let me show you this graph. In US alone, more than 2/3 of the population, we are talking about more than 200 million people, have PFAS contamination in their drinking water. Remember, these molecules don't biodegrade. It means that they can accumulate in the environment and they can find their way to our underground water resources, and they can show up in our drinking water, in rain, and even in the air that we breathe. So this is the scale. I was blown away when I saw the scale of this challenge. This is an interactive map, by the way. I can encourage you to check the link and see if your neighborhood is actually close to one of these basically water treatment centers that are more prone to have PFAS contamination in it. So the question is, why hasn't this important problem been solved so far? And it turns out that what makes these molecules desirable and what gives them the resilience that we need is also the devil that makes it notoriously hard to break. The strong bonds between fluorine and carbon atoms in these PFAS molecules is so hard to break. And it turns out that the reason we haven't been able to come up with more energy efficient ways of eradicating these, eliminating and breaking them down, is that we don't even know, and we haven't had the tools so far to be able to simulate these molecules and to be able to understand what energy is required in this process of breaking these bonds and to be able to basically remove these molecules from the environment. So understanding the energy profile of breaking these strong bonds in PFAS molecules is the critical step to be able to design catalysts that then can, in an energy-efficient process, break these molecules and eliminate them from the environment. All existing computational chemistry methods fail to produce an accurate picture of what happens in this bond-breaking process. You can imagine how difficult this process is, because if we want to, using existing methods, if we want to get an accurate picture of this, we have to diagonalize a matrix that has 10 to the power of 151 rows and columns. It's impossible. But then we realized that we can use Chemist Cloud and the technology that we have created to break this problem into pieces, spin up large volume of cloud instances to solve them in parallel, and then aggregate it to be able to get an accurate picture of these molecules for the first time. When we did our estimation, we realized that in order to do that efficiently and in a reasonable amount of time, we would need more than 1 million CPU cores. At that time, our software was able to scale to a couple of hundred Kubernetes nodes, which basically meant a couple of thousand CPUs. And we realized that in order to be able to reach the point to simulate these molecules, we have to scale up our approach by a factor of 1,000. And that's why, together with Accenture, we partner with the global impact team and the HPC team at AWS and Intel. And we basically got together and defined this as our mission to take the EKS structure and architecture that we have designed Chemist Cloud with and put it on a steroid. And basically, in a short amount of time, scale it 1,000-fold. It has been an exciting ride and collaboration with our partners at AWS, Intel, and Accenture. And I'm really privileged and excited to tell you and share with you that after months of intense collaboration, we have been successful in scaling our Kubernetes clusters in Chemist Cloud to be able to reach 1.1 million compute cores using Intel Xeon CPUs on AWS, so that for the first time in the history of computational chemistry, obtain an accurate understanding of what it takes to break these forever chemicals. Excellent. We are really excited about this result and what it enables us to do next. So this is exciting. This is an exciting moment for our collaboration. But what is really amazing to me personally is that 2-3 months ago, we were only able to scale up to 16,000 CPUs, looking at some of the smaller molecules in the PFAS family. And through this collaboration, and just in a few months, we were able to go from 16K to 1.1 million vCPUs. And I think that speaks to the robust underlying infrastructure that exists on the cloud to be able to take on these high-performance computing tasks and the quality of the computing processors that we are able to get there. So now that we have this energy profile, we are already working with our partners to be able to take this unprecedented result and turn it into a PFAS elimination process that we can roll into market. And we are super excited about this achievement, but what makes us even more excited is that we believe this is just the beginning. What we just did was a proof of concept to show that now by using highly optimized compute processors at a scale on the cloud, we are able to tap into an unprecedented scale of compute that is enabling us to simulate chemistry at an accuracy and a scale that was just not possible before. So why stop at PFAS? There are a lot of other problems that we can use this technology to tackle. I showed you examples of this earlier, but building better perovskite materials for better solar panels, building better, more energy efficient batteries for electric vehicles, finding new filters that are more effective in carbon capture and accelerating drug discovery are only a few examples of what this unprecedented compute capacity on the cloud can unlock. Remember that what we were able to achieve on cloud and on AWS was not possible using traditional and existing high-performance computing paradigms. And now with that, the message that I want to wrap up my presentation with is that the good thing about this is that we built this into our product to enable everyone to be able to get access to it and experiment and study chemistry and solutions to these challenging problems at a scale on this platform. And I wanted to encourage and invite everyone to come contact us to learn more about what this technology is able to do and to brainstorm together and understand what other problems we can solve together in material science using this unprecedented compute capacity. Well, thank you so much for listening to me, and it was a privilege to be able to celebrate this achievement among this audience. Thank you.
Thank you.
everyone. I'd like to now invite Nicholas from IKTOS to share his story with us.
Thank you. Thanks, everyone. Okay, let's talk about chemistry again and drug discovery. So, hi, everyone. My name is Nicolas Dohu. I'm co-founder and CTO of IKTOS, a French company based in Paris. I'm very glad to talk about that project supported by Intel and AWS in collaboration with Medicines for Malaria venture. And in that project, we want to accelerate drug discovery against malaria. Because in a lot of countries, we take for granted that we don't have to worry about diseases like malaria on a daily basis. But in most countries, this is a significant problem. In 2020, there were an estimated 241 million malaria cases in 85 malaria endemic countries, leading to 627,000 deaths. So how can we help? At IKTOS, we deliver AI technologies for medicinal chemistry in order to accelerate drug discovery. And as we already said before, discovering a new drug is not an easy task because of the almost infinite number of possible molecules we can synthesize, and also because a drug needs to have a lot of different properties. And in the whole medicinal chemistry process, this process is made of multiple design, make, test cycles where the chemists try to solve that problem of multiparametric optimization. And it's like trying to solve a very big Rubik's Cube with more than 20 faces. Every time you solve something, you break something else. And that's why AI can really help in that field, using machine learning to predict the outcome of a specific test in silico, or also generative design using reinforcement learning to try to train the AI to create new molecular structures, and also multiparametric optimization in order to solve that giant Rubik's Cube. Okay, so we chose to partner with Medicines for Malaria venture, a nonprofit organization whose mission is to reduce the burden of malaria in disease-endemic countries by discovering, developing, and delivering new, effective, and also affordable drugs against malaria. And their vision is a world in which these innovative medicines will cure and protect the underserved population at risk of malaria and help to, ultimately, we hope, eradicate this terrible disease. Okay, so again, needle in a haystack. With the technology I will show you, we really want to accelerate and to provide a fast and cost-effective solution to virtual screening. So virtual screening is the fact that we need to find in a very big database compounds that are active for a specific, towards a specific protein. And this is very complex because the database is very giant, and we also need to apply simulation on each row on that database called molecular docking, and that this is very costly and that consumes a lot of computing power. Okay, so how do we do that? We do that using machine learning or active learning in conjunction with real docking. We start first with a big database of commercially available compounds from a chemistry provider called Enamine. So it's a 5.5 billion database. We then apply batch processing to filter and compute chemical properties. We end up with a database of 150 million molecules, and that database we want to screen. First, we start with a random selection. We pick randomly 300,000 molecules from that database and use machine learning to build a model to try to predict the result of the simulations. We then apply that model to the whole database and take the best molecules that are predicted by the model. We dock those best molecules and add those results to the dataset, the initial dataset. And we repeat that learn, inference, and selection process 30 times. At the end, we end up with a selection of the best compounds, and we deliver those compounds to MMV. We did that not in 3 runs, but in 2 runs, and ending up with 200 molecules that are in silico the best compound of the database. And what's very interesting here is that we just docked less than 1% of the database thanks to machine learning. So what about the technological component we use? So first, for data preparation on the big billion molecule dataset, we use AWS step functions and AWS batch, also using some chemistry software, of course. And this is a very good technology if you want to scale those kind of batch processes. For model training, we have the chance to work with Intel and Habana Lab to use their latest DL1 instance with their Habana's Gaudi accelerator. And that really impressed us because of the price-performance ratio of that chip. And I will also show you some stats about the acceleration we had with Gaudi. For inference, we choose to go the CPU way, so we scale a cluster of TouchServe server using Intel Xeon processors, and also the IPEX Intel extension for PyTorch for doing inference. And last but not least, we used the AWS Cyclone solution in order to scale the dockings, and we really were very glad to work with Cyclone developers to help us scale on multiple regions the docking simulations. And thank you for that support. So finally, the results. So results so far. So we performed 2 runs, just doing 1 million docking per run, so less than 1% of the whole database. Inference time on CPU was done in 3 minutes. So that's quite fast on just 40 instances. Performance on HPU, it was 30% faster than on the previous GPU we used to work on. And we identified 200 interesting molecules that are now tested by MMV, and we expect to have the results by the end of the year. So thank you so much.
Nicholas, since you're still on stage, maybe the audience would also like to know what were really your considerations for choosing the technology? What was the process you went through to deciding what you wanted to do?
We really wanted to reduce the cost of virtual screening campaigns. So here, it was not a question of using a lot of CPUs and GPUs to do a very massive screening. We really want to have a screening technologies that was able to screen massive database for a very cheap price. So I think the one run costs less than $5,000 on AWS. By screening that huge database, I think it's very, very interesting for non-profits like MMV, because they don't need to launch a lot of instances. So yes, that was the goal.
Fantastic. Thank you so much for sharing your story with us, Nicholas.
Thank you.
So with us in technology, when we've got an emerging technology or a democratized technology that has zero barriers of adoption, that is accessible, this is the kind of stories that we can come alive on. The tremendous, amazing projects that each one of our colleagues here have talked about really tell you how social impact can actually drive the change through the power of technology. One theme that you probably saw through all of these different discussions is really what the collaboration with Intel and AWS actually brings to life. Cloud computing continues to change the curve on what is possible. But what we recognize is that cloud computing requires critical performance. So as high performance actually says, with the central theme of it being performance, it's about cost, it's about dropping TCO, and it's about driving the fastest capability to scale with the power of cloud. And that's really what Intel and AWS want to do, will continue to do. We hope we can jointly engineer, we hope we can jointly optimize, and keep bringing these amazing stories to our audiences as well as our customers. I'd like to invite all three of our experts back on stage and see if there's any questions from the audience.